And now we have the piecewise function. A piecewise function is just what that is. It's a piece of several functions together forming one function. So here, as far as like interpreting values from it, I gotta look at the situation. F of negative 2. Well, I have three different like domains listed in here. Is negative 2 between negative 3 and 3? Well, yes. So I'm going to use the top function. I'm going to use x minus 2 squared. So I plug negative 2 into that. I get negative 4 quantity squared, which equals 16. For f of 5, well, where does 5 fall? Well, is 5 between negative 3 and 3? No. Is 5 between 3 and 5 not including those two n values? Well, no, because 5 would equal 5, and therefore x is excluding 5 from the second row. The third row, I start at 5 and go to 8. Does it fall there? Sure. So if I evaluate f of 5 at this point, I'm going to plug 5 into the bottom function and carry it through. 4 times 5 minus 3, which is 20 minus 3, which equals 17. Last one, I put this in here only because of the fact that I think there's a web work problem kind of similar to this, and there's definitely one out of the work from the textbook you've been asked to do that's kind of similar to it as well. So that's why I'm putting it in here for you to have a look at. What am I going to do with f of absolute value x plus 5? Well, first of all, like any other function, if I have just a number inside the parentheses, my answer is going to be a number. If I have an algebraic expression inside there, then I'm going to have an algebraic expression of some sort as my final answer for, a function like this. So, I'm going to want to, in essence, replace all the x's I see in that piecewise function with the absolute value of x plus 5. I'm going to do this a little bit more systematically, though. I'm going to first deal with the if statements, those intervals I have that define three separate domains for each line of my function. Because what I'm going to do here is I'm going to replace that part of it. And when I look at the results, when I plug in the absolute value of x plus 5 as a replacement for x, the first inequality, that I have for my if statements says that absolute value x has to be between negative 8 and negative 2. Well, that's impossible. An absolute value of something is always going to end up with a positive result. We might put negatives in front of things, when I was doing other problems, but the negative was there because the result of what was inside was also negative, and that would make it positive. I cannot have the absolute value of x be between two negative values. It's impossible. So, same thing with the second row. The assumption the if statement we're working on with there is that the absolute value of x would be between negative 2 and 0, not including 0. Well, that's impossible too. So, since those first three are impossible, I'm going to work under the premise now that I'm going to replace the x with the absolute value of x plus 5 only for the bottom function, 4x minus 3. So that's what I did. I replaced that, distributed. And I got 4 times the absolute value of x plus 17, where x itself was originally between 5 and 8. Okay, that's what the original domain was. The domain would also change over a bit, because the absolute value of x is less than or equal to 3. I could probably say some other values because 0 would be included and all that stuff. I could probably say all results from negative 3 to 3 would work for that, but there's other things that go on with that. So it gets a little tricky, and they don't really care so much about the domain portion. After that fact, it's just, okay, what do I do with this? And that's what you get. So you go from having a piecewise function to have a singular function, because the other two parts just won't work under the premise that you're now creating. How do you graph a piecewise function? First, I set up an XY graph. You notice I have it split into three regions, one for each line of the problem. Then I just use the if statements to pick some x values. So I pick a number of x values. Now, as you see, for the first line, I'm picking a heck of a lot more points than I'm picking for the second and third line. You also see me putting circles around a 3 and a 5 in the center, and I'm going to explain what that all means in a second. First of all, the reason why I'm picking a lot of x values for the first line of problem because it's quadratic. Quadratics are parabolas. So I'm going to want to get an idea of how it curves, what it looks like with respect to the graphing area. So, I'm going to want more than just a couple points. I want to have enough points to see how that curve looks. 2x and 4x minus 3 are linear, which means all I really need are 2 points to compose the line. A big mistake that students make with the second line, x being between 3 and 5, is that I'll have students who'll just pick one number. They'll say 4. Well, there's a lot of numbers between 3 and 5 other than 4. 3.2, 4.9, 3.00001, 4.9999999. There's a whole bunch of them. But if you're only picking 4, you're getting one dot, and you're creating a gap in this graph that's not supposed to be there. There might be some gaps, but you don't want to create a gap that's not meant to be there. So what I often do is I do definitely choose the endpoints, but if I'm not including the endpoints, I just put them in there. So I'm going to put them into that second equation to find out what I'm approaching. And I put the circle there and say, well, I know I'm going to put open dots there. And everywhere I don't have circles, I know it's going to be some sort of closed dot. So, and now I just put them into the appropriate formula. So everything I have, -3, -2, 1, -1, 0, 1, and 3, I'm putting into the first formula. I'm putting the 3 and 5 I have in circles into the second formula. And I'm putting the 5 and 8 I have in the third portion of this graph into the third formula. And when I do that, those are the results I would get. And I would plot and connect the dots appropriately. So, I want to set up this graphing table first because it gives me an idea of how far up and down I have to go. I see my x's go from -3 to 8, so I want to make sure I can at least go that far. My y values go as low as 1 but as high as 29, so I want to make sure I have enough room for that to be accommodated. And here's how I plot the points, and that's what the graph would look like. So you see the three separate parts. Those three separate parts do not necessarily have to be completely disjoint of each other. They could actually connect and be a solid figure. That's what we would say it has continuity, but it doesn't have to be either. So if you have breaks in the graph, it's a good sign you have a piecewise graph. If you have sharp corners in the graph, it's another indication you have you may have a piecewise function of some sort.